In my first video on quantum mechanics, I said that any solution to the Schrödinger equation is a valid physical state of the system. I also mentioned that the Hamiltonian is required to be linear. This has a very important consequence. If you know any solution psi and any other solution phi, then their weighted sum is still a solution. We say that C1 psi plus C2 phi is a superposition of psi and phi. The linearity of the Hamiltonian means that if you know two solutions of the Schrödinger equation, you can describe the system as being in the first state, the second state, and everything in between. If you know even more solutions, then you can describe the system even better. In case of the particle in a one-dimensional box, we even found infinitely many solutions. Okay, now we can describe the system using quite literally uncountably many wave functions, but these are never directly measured. We measure the energy, the momentum, maybe something like the magnetic moment. How do we describe this? The question brings us to the quantum mechanical postulate of measurement. The first thing we need is an operator that corresponds to the quantity we want to measure. For example, for the energy, this is the Hamiltonian, and for momentum it is proportional to the spatial derivative. There are some states that are only multiplied by a constant if you act on them with a specific operator. These states are called eigenstates of that operator, and the constant is called eigenvalue. For example, the solutions we found for a particle in a box are all eigenstates of the Hamiltonian to the eigenvalue En. The postulate of measurement states that if you do a measurement, the system is in an eigenstate of the corresponding operator afterwards, and the value you measure is the corresponding eigenvalue. Well, we just learned that a state can be in a superposition of several wave functions. The sum of two eigenfunctions with different eigenvalues is not an eigenfunction anymore, so what value do we measure in this case? The answer, once again, goes back to probabilities. At the moment of measurement, the system is interpreted to be in either one of the eigenstates that make up its wave function, and mere chance decides which one it picks and which value you measure. This is called the collapse of the wave function. It is this weird probabilistic interpretation of quantum mechanics that prompted Schrödinger to come up with the cat that is both dead and alive. It is, mathematically speaking, in a superposition of both states, and only the process of measurement makes it pick one of the two at random. Of course, this vivid example is extremely oversimplified. For a macroscopic system like a cat in a box, there are so many more effects that play a role, but on the quantum level, this is apparently how nature works. If you find this hard to believe and even harder to understand, you are not alone. I don't think that it is at the moment possible to understand quantum mechanics. This is why we need mathematics. Our brains did not evolve to intuitively get quantum mechanics right. All we can do is to rely on mathematics to give us predictions. That being said, here's some more mathematics. The probability to find any wave function psi in the eigenstate phi of any operator is given by the absolute value squared of the integral of phi complex conjugate times psi. And this is accordingly the probability to measure the eigenvalue of phi. This works for any two wave functions, not just eigenfunctions to a specific operator. The integral inside the absolute squared is called the overlap of psi and phi. The probability to find psi in the state it is already in is 1. This is just the normalization condition we imposed in the beginning. If you prepare the system in the same state over and over again and measure, then the expectation value is given by the sum over the eigenvalues of phi multiplied by the probability to find the system in this state. Finding one expectation value now features the calculation of an awful lot of integrals. But don't worry, everything will become nicer eventually. Until then, enjoy life if you can, and don't be ashamed if you can't.